Alright, welcome back. This is homework 2, part C. I should be a little bit better in camera range than the last video, I realized after uploading, but I can re-record that if needed. I think you can still tell it's me, but if not, I can re-record it. So the question is given that the open bottom diving steel bell is a cylinder with inner radius and inner heights. We also know that there's a uniform wall thickness and one end cap. We're given water temperature and our initial air pressure. And then it wants us to calculate the depth at which the bell and the air trapped inside have net zero buoyancy. And then at this depth, how far into the cylinder does the water encroach? We can start by deriving the force balance and assuming ideal gas law, and then relate hydrostatic pressure to air pressure in bell, and then solve using our coding software. So to start this problem, we can draw a picture. Here is our end cap. Okay. This is our height. That's our radius. Well, we have two radiuses, really, R1 and R2 for the total, because we will need to find this here later on. So, okay. And this is an open bell, open diving bell, but we can draw these, I guess, as well. That wasn't very good. We'll just leave it. So we will start with step 1. I hate that it switches to eraser if I double tap it, but start with step 1 as find volume of the bell. This is going to be V equal to the inner volume plus the end cap. So our inner volume is going to be this here. And that is equal to pi R2 squared minus our R1 squared times our height. And that's because we want, like I said, this here. And then our end cap will be this guy up top. And that will be easier, pi R2 squared is equal to V. So step 2 for this problem, I have decided, is going to be finding the pressure of the water where it is equal to the pressure inside the bell. And that's going to need a picture as well. So this is our tank. This is our bell. Tank has water level, and then the bell has a water level of when it equals out. We can label this as the depth that the bell is submerged. And then this is going to be Z, and because this is the bell, we know that that is H, like it is here. That'll be the same variable. So moving along, we can move these around and then find out what this is based on accounting the weight, or I guess the pressure of the bell, and subtracting our buoyant force. I guess I'll say buoyancy, and then adding the weight from the air and equaling 0. So that takes everything into account, and assuming the net zero circumstance that we've been asked to find. So we know that the weight of the bell is going to be the difference in steel minus the water densities. And that will be times the volume times gravity. And then subtracting our buoyancy force is going to be the density from water times area, but there's a different height here. So that will be Z, because that's the water level in the diving bell. So that'll be this variable here. Get rid of those because you don't really need them. Times gravity again. And then finally adding the weight from the air, which is going to be the air density times area times gravity, but instead of Z, it'll be H minus Z to get this distance. And again, equals 0. So this we will box in and save for later. It's a little crooked. So then step 3 is going to be using our ideal gas law assumption, PV equals nRT, and we're relating initial to the hydrostatic. Hydrostatic. All right, so our initial, I'm going to label it as pressure naught, HA, so that will be before it's submerged. So when it's not underwater, is equal to nRT. Because this is a given, we don't have to substitute. There's nothing else to solve for P naught. So then for our hydrostatic, we can do pressure is equal to area, but again, it has a different height, and that height can be shown as H minus Z. So that'll be this guy once it's submerged at the depth drawn. And that is equal to nRT. So for this pressure, we can substitute out that of the hydrostatic pressure. And that pressure is going to be equal to the density of water times gravity. And then for our height that we want to use this time, we will be using the depth minus our Z. So D minus Z, and that will be our hydrostatic pressure. So substituting this into here for what we just solved is going to look like this. Rho W G D minus Z times area times H minus Z equal to nRT. So because nRT is now equal on both sides, we can set this equal to this. So that will look like P naught HA is equal to rho W G, difference in D and Z, times A times H minus Z. So like I said, that's just doing this and setting it equal to this and kind of canceling these, I guess. We can also cancel the area and rewrite a simplified equation that relates our pressures. So P naught H equals rho W, gravity, D minus Z, and H minus Z. So again, we can box this in and save for solving. So, I wanted to turn it so it's a little bit better seen. So that is the deriving equations for 2c.